Okay, so now that we've established what a function is and how to tell if something is a function or not, we're going to get a little more specific. Now, keep in mind in this class, we're talking about a lot of different types of functions. The first one we're going to get into here is a linear function. It's the most basic. Once you learn the easy method to graph them, it's pretty quick because all you need are 2 coordinate points to graph any given line, and we'll talk more about that. So again, objectives here is we're just going to identify a linear function using a various amount of things. We're also going to start to graph linear functions and talk about discrete and continuous data. And in a lot of these things, we're going to see some real life problems. A linear a linear equation in 2 variables, x and y, is an equation that can be written of the form y equals mx plus b. Now, we're going to dig more into this later, but this is going to be kind of a big thing that pops up here, this y equals mx plus b. And if you could just get that in your notes now as slope-intercept form, slope-intercept. That is going to pop up again and again throughout the course of the rest of the year. So we almost need to have y equals mx plus b ingrained into our memory here. It says m and b are going to be constant values, meaning they are not going to change. We're going to have an input x and an output y that will change from inputs and outputs depending on what we plug into them. So we have a linear function is a function whose graph is a non-vertical line. Again, a vertical line is the way we test if something's not a function at all. So a vertical line is not a linear function because it's not a function. It is something that we use from time to time in this class, but it's not a linear function. A nonlinear function does not have a constant rate of change, so its graph is not a line. So if it's a vertical line or not a line on the picture, it's not a linear function, obviously. So some of these things are going to be pretty self-explanatory as we go through this section. Pretty easy here to tell. The one on the left is not a line. The one on the right is a line. So you can say nonlinear, linear, and you can use the explanation as simple as it's not a line. With tables, it's a little different. There's a constant rate of change along the top and the bottom with sums or differences. So in this example, on the left side, we have along the top, the variables inputs are increasing by 3 all the way across. So we have plus 3, plus 3, plus 3, and so on. Along the bottom, we're going down by 6 every single time. Now you have to check and make sure that it goes all the way through. So minus 6, minus 6, minus 6. I will tell you I trick a lot of kids on quizzes because this last one is not always the same. So watch for stuff like that. So this first example is a linear function because it has a constant sum or difference across the bottom. The top function, again, you're probably going to see the same thing across the top every single time. So we increase by 2 across the top. That's not going to be what we really pay attention to. What we really need to watch is the outputs. So we go from 2 to 9, which is plus 7. Then we go from 9 to 20, which is plus 11. And from 20 to 35, plus 15. Not a constant rate of change. So we can say that this one is non-linear. And you don't need to figure out what it is at this time. We just are gonna for this section say nonlinear. So again, we're to one of those parts in the videos where you should pause in your notes and try these examples. Make sure that you understand it. It shouldn't be too hard. I'm going to go ahead and answer them now. Again, we have the first one here. It's a straight line, so we have yes. We can say linear. We can say non-linear for the sake of time here. I'm just going to put non-line. Looking at our constant rate of change again across the top, it's going up by 1. Across the bottom, plus 2, plus 2, plus 2. So because that is constant all the way through, we can say that this one is also linear. Across the top, again, it's always going to be the same. Across the bottom, we go down by 8, then we go down by 4, then we go down by 2. Something to kind of think about here is this a function this type of graph, is there a pattern here that we could use in the future? So we know it's not a common sum or difference, but is there something else going on here? This might be something that we see a little bit later on, and you might have to explain what's going on here. In example 3, here's the basically the easiest thing I can tell you guys. In linear functions, you're going to have basic linear functions are going to look like this: y equals mx plus b. Now, let's just say that we have numbers where we normally would have numbers. So let's write a for instance here: mx plus b, let's say 3x plus 7. Again, keep in mind 3 over 2x keep in mind 3 over 2 and 7 will from time to time be different values. But really what we need to look at is our input variable for linear functions. Our input variable in any linear function is going to be a variable to the first power. So when we look at this, first of all, we don't even have an input variable in this very first example here. This function, this looks like a bunch of gibberish. This function, this first example, we have y equals 3.8. There's no input variable whatsoever. So what this function is actually called, and you could argue that it's a linear function, but because we don't have a variable at all, we're just going to call this a constant. The book will refer to it as a constant function, but basically what this is, without an input variable, is you have a horizontal line. So if this is my x and my y axis, I have a horizontal line through 3.8, and it looks like that. Now, again, it's still a line, but we don't have an input variable, so we're going to call that a constant function, not a linear function. Looking at the second example, we have this function y is equal to the square root of x. Now, we haven't really dealt with very many radicals for the most part, but we know if it's underneath a radical symbol, the power on the x itself here, you could look at it as a 1, but also the square root of x can be written as x to the 1/2 power. So this is not a linear function. So the first two are constant, and again, you can just say nonlinear for the time being. This will be a function that you'll see at the end of the year, though. This next function, we have y equals 3 to the x power. Again, I want my input to be to the first power. In this one, yeah, the input's to the first power, but if we notice, it's a power itself. That's not a linear function either, and that's going to be something that we look at a little bit later on in the year as well. The next one, you guys, we have a bunch of non-examples here. The next one, we have y equals 2 over x. Now again, we can say x is to the first power, but when it's in the denominator, we have some properties of exponents where if I want to write this up high with that 2, this is actually 2 times x to the negative 1 power. So it's not to the first power if we write it properly in function notation, which is like this right here. We want it to look like that. The next one, now here's the thing, we want it to be able to look like y equals mx plus b. So if I were to rewrite this function and do some math operations to it, 6 times x minus 1, I can distribute this 6 through the parentheses, and I get y equals 6x minus 6. Now I can make this function look like that, and my variable is to the first power. So yes, this one, in all of these functions, this one is the only one that is a linear function. And if we look at this next one, we can see pretty easily that we have y is equal to x squared if I were to isolate the y variable like we should know how to do. And that is also not a linear function. So basically, the big thing to watch for, you guys, is my is my variable to the positive 1 power, or is my variable an exponent? And if it does either of those things, if it's a negative power or an exponent variable, it's not a linear function. Look for the variable to be to the first power, and you should be able to write it in function notation. If I were to isolate my variable y, I should be able to write it in the sum form of y equals mx plus b. That's the real way you can tell by looking at a function if it's a linear function. So looking at these pretty easily, I can see right away number 5. Again, pause this, try this, think about it for half a second. and see if you're right. Again, ask questions when you're not and make sure that you understand what's going on here. But I can see pretty easily here that I have this already in function notation. Y equals mx plus b. Well, I could call my m1 and my b9, and number 5 is, yes, it is linear. So linear. Number 6, again, I can write this in function notation. Y equals 3x over 5 can also be written like this, 3 over 5x. That's exactly the same thing. If I were to multiply fractions, 3 over 5 times 2 is the same as 3 times 2 over 5. So yeah, that's a linear function as well. And then right away on number 7, we should see a red flag. I have the x to the second power, not a linear function. And again, we'll see those later on in the year. So anytime you see one of these in the notes, whether it's in one of my videos or in the notes, this is something that you're going to want to pause and copy down. We've talked about a bunch of different ways to tell whether or not something is a function, and now we've narrowed it down to a linear function. Again, if it's in a table, you have a constant rate of change with sums or differences. Key words, sum or difference, not product or quotient. So it needs to be adding or subtracting across the outputs. The variables that are the inputs are always going to be constant. That's what always happens. We plug in numbers right next to each other. So make sure that's a constant rate of change. In a mapping, again, your outputs need to be a constant rate of change. In a graph, it's pretty easy. Is that thing a line? As long as it's not vertical, you can say it's linear. Again, more core concepts here. You can copy down these definitions, really just look them over, make sure you understand what's going on. The core concept here with discrete and continuous, here's the best way I can explain it. With things that are discrete, you can't have parts of them. So for instance, let's come up with an example of a discrete number of input things. Things like, I'm going to take so many kids on a trip, and for every kid that I take on this trip, it's going to cost me $25. So for every ticket, let's say that I'm buying tickets for these kids. For every ticket that I buy, I'm going to spend $25 more. This is a discrete domain because I'm not going to buy partial tickets. I'm not going to take partial students on this trip. An example of a continuous domain, we could talk about maybe the fuel that's getting burned in my vehicle as I'm going down the road. It's not burning exactly in gallon intervals. For every mile you travel, it burns a little more gas. So that would be an example of a continuous domain. When you're listing domain and range for things like this, that's going to be the difference in whether for a discrete domain, for example, for the top one, my domain would just be those numbers, 1, 2, 3, 4, and so on. For a continuous domain, your domain would look like this. All of the numbers and any number that exists between, and it's going to be between 1 and 5. So you could have fractions, decimals, anything could be there. 1/100th would work here. Or 1 in 100th, sorry. But that's the difference in the domain and how you list those numbers in these two. So I'm going to just talk about these problems here. And again, just so long as you understand, look at the problem and tell me what's going on here. So this is perfect. This is the ticket example I just got done talking about. We should know right away, for each ticket I buy, I'm going to spend another $15.95. This is going to be a discrete domain. So when it asks for what the domain is, you can say it's 0, 1, 2, 3, and 4, and it's discrete. When you find the range, I can list these exact numbers right here, 0, 15.95, 31.90, and so on. Those are the exact number, or the exact amount of money I will spend. Example 5 is a little different. It says they have a cereal bar that has 130 calories. Now again, I don't have to eat exact intervals of cereal bars. I could eat half, I could stop after one bite, and so on and so forth. So if I look at this, when I'm listing my domain here, I'm going to say my domain as an interval between 0 and X, and however many candy bars I eat, let's just say 5 is the maximum in the box, that would be my domain. Likewise with my range, pick a little more favorable color here, my range is also going to need to be an interval. It will be 0 less than or equal to y less than or equal to whatever the number is here. So for this, it was 520. For 5, it would be something different, but it would be something like 520. So that's the difference in when we talk about discrete and continuous data, how we list our domain and range. So again, just take a minute to think about discrete or continuous. If you want to challenge yourself to try the domain and the range, that's great. But I really want you to understand the domain and the range, whether they're discrete or continuous. So talking about this is number of stories of a building in number 9, and then a 20-gallon bathtub is draining in number 10. So you just take a second, think about, is this discrete or continuous data? Okay, so number 9, hopefully when you're building a building, you're not going to stop halfway through a story and just leave it that way. We're going to be discrete on number 9. So your domain would be 1, 2, and 3, and your range would be 12, 24, and 36 for the heights of those stories. Number 10 would be a continuous. Again, you can stop draining the tub at any given time. It drains at a constant rate. So you have a 20-gallon bathtub. So y equals 20, the initial gallons that are in there, minus 2.5 times x. And if you wanted to put a function together and a table together like number 9, you sure could. But your domain and range would be like 0 is less than or equal to x, which is less than or equal to 20. It's not going to go any farther than 20 gallons out. Same thing for y. It's going to be the exact same range. So again, hopefully you guys understood this. Ask questions if you have them. Make sure that you took some time and wrote down some of those notes. Go back to the video, pause in the core concepts. Make sure you have that down so that you really understand it. Good luck. Have fun.